Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about another algorithm design technique called dynamic programming. I'll abbreviate it as DP. So you might ask, what is dynamic programming? So by the end of today, you should have a general idea of what dynamic programming is, and depending how far along we get, we'll get to see some examples of how these concepts are first proven, but also the general idea of them. So we'll see some examples as well. So just before everything, I want to give you kind of an overview idea of this. So what we're going to do is we're going to attempt to solve a problem. Typically, this will be an optimization problem. What we want to do is we want to combine solutions of subproblems to obtain the optimum. So one part of this should sound very familiar to you. It should remind you a little bit about when we talk about divide and conquer. In divide and conquer, we take the subproblems, we break them into those pieces, and then we solve all of those until they're smaller, sufficiently small. Then we conquer them by putting them all together, right? At the end. This sounds quite similar to that idea, except I must stress that dynamic programming is suited best for when you have overlapping subproblems. In fact, the conditions of dynamic programming essentially require it. So you'll see what I mean when I say this. But I want to talk about the first real big concept that really matters when we talk about dynamic programming. And the first one I'll mention is principle of optimality. I'll talk more about that in specific detail, but the one I really want to focus on right now is what we call memoization. Now, I must stress that is not a typo. It doesn't say memorization. It says memoization. Now, you might ask, what is memoization? So if you're looking at this word and you're like, what does that mean? So it's actually the combination of two words, memo and memorization. So if you take those two words and slam them together, you get memoization. And you might ask, why does this matter? So let me explain what the concept of memoizing is. So what it means is, suppose I give you some problem, and I'm trying to solve some part of that problem. What I can do is I can store the solution to that subproblem so that I can use it again if I encounter it. So the idea is very simple. To memorize means to store a solution to a subproblem in a table. And next time I see it, I could just look in memory. So if I can identify that subproblem again, instead of solving it all over again, I just look in the table to check it. So just to give you the idea really why you might say, okay, well, why is it this? It's a technical jargon term for basically the idea of this. Now, if you've ever seen a memo before, these are typically notices that are sent out to employees or other colleagues to notify them of some detail or instruction sometimes. For example, you get into the workplace, there might be a memo sitting there on the door or somewhere in the office on a notice board, and usually employees go check that out before they go do tasks they need to do. So, or there might even be an electronic version of this. So for example, suppose I gave you, I was a manager or something, and somebody told me, okay, at some point somebody's going to ask you what 2 plus 2 is. So what I could do is I can write a notice for myself that I could give to anybody, including myself, after the fact, that I'll just post it here and say, okay, the answer to 2 plus 2 is 4. So whenever somebody asks me what 2 plus 2 is, I don't have to calculate that out. I just look at this memo here. It's kind of hard to see, but it says 4 on there. So you could think of it like every time I need to figure out an answer to something, I can look it up once. So when I first calculate it, I make this notice, and then all I do is if ever I encounter it again, I check first here before I attempt to do it myself. That's why we're calling it memoization, because you can think of it like I'm appealing to this memo, but I require to know about it. So it's like memorizing some memo. So hopefully the terminology makes sense to you, is that I'm taking the idea that I'm going to use some space to help me compute something so that I don't have to recompute it again. Does everybody understand the idea of what I mean by Memoize? Just to be clear. Okay, great. Great. So that's really one piece of this dynamic programming puzzle. So now you might ask, Dan, what can we do with this memoization business? So suppose there's a couple clever, very useful ways of using memoization. So memoization is this concept that is broader than just dynamic programming. Very often, if you find yourself running into a situation where you know the answers to some sub-problems, or you're computing them, but you're doing it very frequently, you may take advantage of this memoization idea. So a very good and applicable situation for something like this is that you can always cache those previously computed results, and basically, yeah, it's a lookup table. So yeah, just like when you're doing, say, arithmetic like this, I have addition, I can make a table that I can appeal to as opposed to calculating it out myself. But there's a trade-off. So there's a trade-off when I do this, right? So when I do this, I have to have a table that I can look up to. So I'm expending space to save myself time. So just keep that in mind when we do this. So in the circumstances when we look at dynamic programming, it's really going to work in our favor. So there's an adage that typically computer scientists like using, is that you can reuse space, but you can't reuse time. So we're trying to use this adage to help us compute things faster. So we use some more memory, but there's obviously a trade-off to this. You can't make yourself a table that's like exponentially huge and expect to say, hey, look, this is a really efficient algorithm. Because what happens is if your table's exponentially big, you have to build this table at some point. Now, it would be nice if it was just done once, but suppose I give you any arbitrary instance, every time it might have to build this table at the beginning. Or it might be a key part of the algorithm, which is what's going to happen very often in dynamic programming. So you're going to see that there's this relationship that allows us to have it where we can expend some space, so we don't have to worry about recomputing things. But let me just kind of contextualize this for two kind of, what I would consider killer applications for memoization. So the first one is that if I give you a recursive algorithm, which these are inherently top-down in the way that we usually view them from a divide and conquer standpoint, where I start off with a general problem, then I subdivide it into smaller pieces, and then I solve those smaller pieces. What I can do is I can use memoization to cache those previous results, so if ever I encounter it, I don't have to recompute the whole thing myself. If I already encountered it before, I just look up in the table first before I attempt to calculate it. So this can be used to speed up recursive algorithms. But the way we're going to use memoization, this is the most important piece for us, is suppose that I had several of these notes here. And all of these gave me answers to things that I'm going to need for my calculations. So what we're going to do is we're going to tabulate results that are going to be optimal solutions to subproblems. And then here's how dynamic programming is going to use these. Is imagine I have a series of these memos, and they give me the information I need to compute a larger subproblem. Because of this thing I'm going to call the principle of optimality, I'll lovingly call it with the acronym POO, which I'll get to in a moment. What I can do now is I can use the table to help me compute larger values in the table. So I don't ever have to recompute anything. Instead, I'm going to use those tabulated results to build a solution, and the method for which I'm going to do this is bottom up. So dynamic programming is a bottom up process. It's not a top down process like divide and conquer. So you've got to think about dynamic programming, at least the way that I'm going to show you it here, you think of it as a bottom-up process. So I'm going to start off with smaller, like the smallest subproblems, and I'll show you ways you can combine the solutions of those so that you can get to your given problem. But a key part of this is this overlapping subproblem phenomena that we have. There's also one other piece to that. Isn't it interesting? So this is one thing you can always take advantage of, because a lot of our algorithms, we just don't really use that, right? So this is something that's in your cap that you can use. So let me proceed to doing a first example just to illustrate the difference. So let me just move on over here. Okay, so I thought we'd keep something very nice and simple, as I'm going to be interested in computing the nth Fibonacci number. So you might ask, Dan, what's a Fibonacci number? You may or may not know what a Fibonacci number is. It's one of these classic number sequences, but I'll define it for you. This is one classic way of defining it. So here's the idea. So I must stress that there are other formulations of the Fibonacci sequence, but here's how I'm going to define it for you. So if I want the nth Fibonacci number, what I do is I take the previous Fibonacci number and I add it to its previous Fibonacci number. So I take, for fib of n, I have fib of n minus 1 plus fib of n minus 2, if n is greater than 2. And I define these two base cases here. Fib of 1 is 1, fib of 2 is 1. I must stress that another way you can also define the Fibonacci sequence is by having a 0th Fibonacci number and have it so it's defined as 0. But this will work fine for what we need here. So are we all okay with the definition of a Fibonacci number? So just to be clear, what you should expect this to be is that the sequence will be 1. So this would be the first Fibonacci number, this is the second Fibonacci number. The third one would be the sum of the two previous ones. So it would be 2. The sum of the two previous ones for the next Fibonacci number would be 3, and so on. So what I want to know is the nth Fibonacci number. So I want to compute this recurrence. So from the way I've described it here, I can actually naturally write out an algorithm for you based on this recurrence. So here's an example of how I can formulate this. So here's an algorithm. I'll call it fib n, just because I've used fib over here. As input, it's going to take a positive integer, n. And as output, it's going to give me the, I don't know why I was writing a t like that. That makes things fun. Output is the nth Fibonacci number. So all I do is I look at what this recurrence says, and that's quite quickly how I'm going to write this out. So I know that if n is less than or equal to 2, we know right away how to compute this. We know that it's supposed to be, the answer is supposed to be 1, right? So if n is less than or equal to 2, you're just going to simply return 1. So I return 1. Otherwise, little squeaky marker. Otherwise, we're going to return just the sum that I have over here in our recursive case. So this is our base, these are our two base cases. Here's my recursive case. So I'm just going to write that out right here. Fib of n minus 1 plus fib of n minus 2. Squeaky, squeaky marker. Hopefully that isn't bothering anybody. If not, just let me know. I'll try to switch the marker. Okay, so here's an algorithm for computing the nth Fibonacci number. So it's naturally written out in a recursive manner. Now, you might ask, Dan, what's the running time for this algorithm? So let me just show you what the call tree for this would look like. So just let me just show you how this would execute if I gave you fib of 5. So let me just do fib of 5. So if I give you fib of 5, well, computing fib of 5 depends actually on results. In fact, it depends on two results, right? Depends on fib of 4 and fib of 3. If we look on the right side here, what do I need to compute fib of 3? Can somebody tell me? Yeah, 2 and 1, exactly. I'm going to need fib 2 and fib 1. Fib 2 and fib 1. So notice that these are 2 base cases, so we don't have to do anything more here on the right side of the tree. However, on the left side, you're going to have it where we're going to depend on computing fib of 3 and fib of 2, which naturally I'm going to need, so I'm going to need fib of 2 and fib of 1 right here. So this would be an example of its call tree. So to compute out fib of 5, I have to make all of these recursive calls. So do you see something that's really kind of peculiar about this tree? Something that you would say, Dan, that's kind of silly. Why would you do that? Like, why would I do this? Does anybody have any ideas of anything that looks kind of peculiar I'm doing here? Yeah, notice I'm calculating things over and over again. Notice that I have fib 3 here. Fib 3 is right here. Fib 2 is, well, fib 2 is just simply a base case, but notice that a lot of the nodes in my call tree are repetitions of each other, right? So I'm repeating a lot of work when I do this. So notice there's a lot of redundant computations here. In fact, if you were to analyze this algorithm, notice that if you were to look at this and say, okay, if I ignore the recursion, okay, this looks like a constant amount of operations in the recursive case. In base cases, it's still constant, right? So if you were to look at that call tree, there's actually a mirroring recursion tree for this, that if I give you an arbitrary n, notice that if I look down the left side, all the way down the leftmost path, notice that it always decrements by 1 in my tree, but every single time on that leftmost side, it always expands with 2 children every single time. So if somebody were to just come up with a rough calculation of the running time, does anyone have any ideas of what the efficiency of this algorithm would be? Like what its running time is in the worst case? It could be big O, it doesn't have to be big theta. It doesn't have to also be the tightest of results. So I'll give you a hint. So imagine if this tree always split like this with 2 children, but did it everywhere. It is exponential, indeed. It is exponential. So you can show, using the recursion tree method, that this actually, this algorithm that I've just described to you, its time complexity is going to end up being big O of 2 to the power of n. This is actually because of just how the children get expanded out. But I also want to stress one small detail that you might ask, okay, well, where did that come from? Like I said, every time it splits on 2, but it does, if I imagine this happening everywhere, then you notice it'll look like a proper binary tree all the way down. But in fact, it'll also be where every level is full, if I were to bound it from above. So remember I mentioned that with the recursion tree method, you sometimes also can bound the amount of work that happens at a level? That's exactly what I'm imposing here. Is I'm saying, okay, at every level, it's going to be a power of 2 when I say this. Because you would agree with me that when I get down here, Most certainly a nice bound on the running time would just simply be, okay, imagine if this had 2 children, that had 2 children, and that had 2 children. And you could sum this up like, actually it's quite similar to something you're actually doing on the final assignment actually. So I won't tell you too many details about that, but you don't, in that case, don't have to bound anything really. In this case, you would. But I must stress that there is actually a tighter running time for this. It's actually that it's big theta of the golden ratio to the n. Or if you're wondering what the golden ratio is, the golden ratio is 1 plus the square root of 5 over 2. So let me just write that out a little bit more carefully. And if you're wondering where it sits in all of this, the golden ratio raised to the power of n is sandwiched in between 2 to the power of n over 2 and 2 to the power of n. So if you're wondering why I kind of was like, okay, well, imagine if I assume that all the children all were exactly 2 on the internal nodes of this tree. If you take the opposing case, you get this bound, where you get it as 2 to the power of n over 2. So you could say that the running time is big omega of 2 to the power of n over 2. But yeah, so notice that this is exponential, right? That's not very good. So believe it or not, one strategy you can take to do that, to remedy this issue, is using memoization. So notice that instead of me just straight up going right to this line and computing fib of n minus 1 plus fib of n minus 2, I can always introduce an array that looks up the nth Fibonacci number in that array. So if I put that right before this and I check, is there an entry in a spot where the nth Fibonacci number would be for that recursive call? And keep in mind, in the context of this recursive algorithm, this would have to be something you've declared outside the scope of the recursive algorithm. So this would be something that you're hanging on to by pointer, or it'll be something that's declared outside the scope of the recursive algorithm. So why? Because every time you make a recursive call, you don't want to have it where it's creating a brand new array every single time. That's also not a good idea because it won't store all of your previous results either. So that's one way you can use memoization, and that would indeed deal with your situation where we're having all these repetitions happening. What instead will happen in that case is the first time you compute fib of 3, it'll compute fib of 2 and fib of 1. These will fill in the entries for fib of 1, fib of 2, and fib of 3. And then whenever you get to computing fib 4, or if you start on this side, which in this case it will, you'll appeal to our table or lookup. They look at fib of 3, fib of 2, and fib of 1. Now that's one way you could do this, but that isn't really, in my opinion, this is just my opinion on this, that's one way you could speed up this algorithm, most certainly. But you notice I'm still doing a whole bunch of recursion, right? So what if I had told you there's a much simpler algorithm for computing the nth Fibonacci number, that instead I use smaller instances of this problem to build up to the nth Fibonacci number? So I'm going to build the nth Fibonacci number bottom up as opposed to top down. So if I use memoization to look up in this table, I'm still doing a top down process, just I'm saving myself time by having this little bit of memory to help me look things up. So let me show you how I'm going to employ dynamic programming. So watch this carefully. First, before I proceed, are there any questions about anything I've just described over here? Because I'm going to show you how I would approach this with dynamic programming. And you'll be saying, damn, why didn't we do this from earlier? It's because I need to motivate you by showing you a bunch of different other techniques too. But yeah, so let me proceed then. So let's go this way. I'm going to shuffle on over this way. Okay, so let me show you what I can do with dynamic programming when dealing with this circumstance. So all we're going to do now is I'm going to allocate an array of length n. So here's the idea. So here's a better approach. Here's a better approach. So we're just going to allocate an array of length n, and use it to store previous values of fib. Kind of an unfortunate name because fib is also something that you'd say like, yeah, it's kind of a little bit of a lie. As we go until we compute fib of n. So here is our simple dynamic programming algorithm. And you're going to ask, Dan, why did I do all that over there? Like I said, it's just to illustrate that there is other ways of approaching something like this. So here I'm going to describe the algorithm. And you're going to say, Dan, this is going to be deadly simple, isn't it? And it is. And it is. This is something that first year you could have easily done yourself. That's just to illustrate the ideas. So I'm going to call it fib dp of n. And output are going to be the exact same I had over there on the first example. So they're going to be the exact same. So I'm going to start off this process by creating an array of length n. So I'm going to say fib is just going to be, so I'm going to show you a couple different ways I'm going to declare arrays just for the sake of you seeing a couple different ways of writing it out. So fib is going to be where I'm going to create a new integer array, of length n. And I'm going to presume that I'm indexing this array from 0 up to n minus 1 in the typical way. And then all I'm going to do is I'm going to have a loop. And here we go. So I'm going to go for I starting at 1 to n. We're going to do the following. So all I'm going to do is I'm just going to rip out what I had over there before, and instead I'm just going to use my array to store those smaller values so that I can build the larger values. So if n is, sorry, we don't want n now. Now we want I, because we're going to be building up to fib of n. So if I is less than or equal to 2, then we know the answer for the first two Fibonacci numbers. We know that the answer there is 1. So just do note that if you're wondering why I'm putting I minus 1 there, it's because of the indexing for this array. It starts at 0, and notice that the indexing on my loop starts at 1. Else, I'm going to have it where I have fib of I minus 1 is just going to simply be what I wrote as definition of the, in our case, the ith Fibonacci number. Fib of I minus 1 plus fib of I minus 1 minus 2. And that's the end of this loop. And then all I do is I return the last position in the array. So I just return fib of n minus 1. So I encourage you to convince yourself that this algorithm indeed works. So try it out on an array for an nth Fibonacci number in your spare time. But does everybody see that this, so is everybody convinced that this algorithm in fact computes the nth Fibonacci number? Are there any questions about it? So notice that I'm using some memory to help me do this, but notice the way I'm doing it. I'm building up to the nth Fibonacci number starting at my base cases. And then I use that information to build the next Fibonacci number. That's the big idea here. So I'm memoizing. It sounds like I'm talking to you like I'm like 4 or something with a little bit of a rasp. I'm like, it's a memoizing, but I do that anyway, so that's sort of the fun with this. So anyways, I have, so I start off with these 2, and then I'm going to build up to the nth Fibonacci number by computing the ith Fibonacci number. And then by using this bit of memory, this saves me time. Can somebody tell me what the worst case running time for this algorithm is? Yeah, it's n. Yes, so it's big theta n time. You might ask why? Okay, so we create a new integer array of length n, so you know that's going to take linear time. Then I have a loop. It does n iterations. In each iteration of the loop, this is a constant amount of operations that happen in here, regardless of which case it falls into. So I have n iterations of a constant amount of operations. So regardless, it's going to be big theta n when I add up all those operations. Okay? So this is one of the main ideas behind dynamic programming, is reduce those repeated computations by using a bit of memory. Like I want to reiterate, and I'll write this again. Just watch, I said it earlier, but remember, this is the tip I really want to get across, is you can reuse memory. You can reuse memory. You cannot reuse time. And I'm not assuming any weird sci-fi scenarios here, okay? So we're trying to take advantage of this fact, plus the fact, and this is what this so-called principle of optimality is about, is that I can write the answers with respect to answers of smaller problems. In this case, notice that to compute the nth Fibonacci number, I can express it in terms of the n-1 Fibonacci number and the n-2, it's kind of funny to say, n-2nd Fibonacci number. And I can do this for any arbitrary n. If we could just use the last 2 results, it will still work, right? So I guess tech, because keep in mind, we still have these base cases we're going to need. Let's see, the 2 results. I'm not sure exactly what you mean. If you can clarify that for me, I can happily answer it. But the big idea here is that we're going to be showing this thing called the principle of optimality, which is going to be the key thing that we're going to use when we're designing our dynamic programming algorithms. So one part of this is this overlapping subproblem aspect, which is one element of the principle of optimality. But we're going to also have this memoization process where we're just going to use some memory, but we're going to be using it in combination with the principle of optimality. Those 2 things together is what makes the dynamic programming technique work. And I must stress that not every problem satisfies this principle of optimality criteria. Just like when I talked about greedy algorithms, remember I talked out there and I said, oh, there's only certain problems you can design efficient greedy algorithms for because they rely on structure of that problem. So it's going to be no different here. I have to show you that some property holds for that problem. So this requires me to prove that to you. So is that clear, everybody? So in the way that traditionally people talk about dynamic programming, it's an inherently bottom-up process. Notice here that I always, to describe the solution, it's always in terms of smaller subproblems. But I must stress that there's also a more colloquial use of dynamic programming that some people refer to as top-down dynamic programming. That is actually what I was describing earlier. where what you do is you have your recurrence relation, then you use memoization in combination with your recursive algorithm. That's what some people call top-down dynamic programming. So in some schools of thought, they say that's dynamic programming too. But me, I'm more of a purist. I like to think of dynamic programming as a strictly bottom-up process, because that's usually how we like to think about it. Okay? But yeah, no, the way that we got to think about dynamic programming is that we're combining these smaller subproblems to get an answer. So what I'm saying is more of a practical consideration of the same theory. But hopefully that clarifies that. Okay, so I want to now describe to you the principle of optimality. And you'll see why I describe it as this thing that is bottom up. So I'm hoping this will clarify any confusion if there's any. So I must stress that there's other ways of framing the principle of optimality. There's just to give you a little bit of fun backstory about this. So this concept of dynamic programming was first formulated by a fellow named Richard Bellman. And he was doing this within the context of the mid 20th century. And in the rays of those days, this type of mathematical programming techniques, or these algorithm design techniques as we would call them today, all the craze at the time was things like linear programming. If you've ever heard of that, it's very much the name when you hear programming in this context is referring to planning, just like in linear programming, which is also about planning. That's at least the original formulation of that name. So it's in a more military-esque way of using the word programming. But other people use programming now in today's world in a very more casual way. Talk about TV programming, for example. So in the context of Bellman's work, Bellman was working at the Rand, which is effectively these days you can think of it as a think tank for the American military. And Bellman was looking for a natural way to talk about these optimization problems, and he came up with this, what we're calling the principle of optimality. And Bellman, now this term is often used in different contexts, whether you talk about economics or some types of engineering. Sometimes it's called Bellman's equation. But it's described in more as a dynamic decision process, a multi-stage decision process. The way we talk about it is typically within the context of an optimal solution, because we're really interested in solving optimization problems. You can look at our typical case, like our Fibonacci over here, is a very specialized optimization problem where it only has one answer, as opposed to there being potentially many possible feasible answers, or possibly even multiple optimals. Okay, so the fun story around Bellman is that, at least this is the folklore around it. I can't remember how well documented this is. I'm pretty sure it is that he essentially called it dynamic programming just off the name of linear programming to help get funding for his work. So that's just sort of the fun story behind it. Because I mean, when you talk about these weird, because remember, in that time period, computers were still very much this thing in this infancy. So for someone like Bellman, this very much was an idea that was very abstract. It was not very something easy to market in those days. So we're going to talk about the principle of optimality. And I'm going to lovingly acronize him as poo. I must stress that most people don't acronize this thing as poo. I do it because it makes you remember it easier. That's my little bit of, if you want a little bit of insight into my method of madness, is that I'll lovingly refer to it as poo in this class. But here's the idea of what the principle of optimality is. The principle of optimality is said to apply to a problem if an optimal solution to an instance, so when I'm saying instance, I'm talking about an instance of the problem, to an instance always, now this is the most important part, always contains optimal solutions to all sub-instances of that instance. Now, if you're wondering what that means, because I've never used this phrase sub-instance before, so imagine I give you a series of items, for example. If I tell you that my answer is optimal and it's a collection of items, as we're going to see in one of our examples coming up. If I remove one of the items from this, what I can say, because this property, what I'm saying is if I remove any arbitrary item from my solution, from my decisions I made, it must be that whatever I'm left with, if I look at the instance where I removed this item from the instance, so I only consider the sub-instance, that is in fact what I've just presented to you is also an optimal solution for that sub-instance. And I could do this for any one item of my optimal solution. And this applies downwards as well. So for example, if I then have that solution, I can pull off an item there. And I could keep doing this process down and down. And every single time it's going to be an optimal solution. So another way you can phrase this, and this is the way that you'll find in a lot of modern textbooks, will tend to say this, or if you look this up online, they'll very much say the following. So this is the technical way of describing it. There's a much more fundamental way of describing this. This is more like Bellman's original formulation. In other words, a given problem has overlapping subproblems and optimal substructure. So we already talked about this overlapping subproblem case, like I talked about with my Fibonacci example, and like what I just described previously. That when I take parts of my problems and decompose them like I just described, each one of those is in fact a solution to another instance that, for instance, if I were to remove that item, that's also an instance to my problem. So that's what I'm referring to as overlapping subproblems. Optimal substructure is also another way of me saying what I just said above here. If I remove an item from my collection, then most certainly whatever I'm left with, for some instance that only consists of the items I've kept there, that is also an optimal solution. In fact, we've encountered this property before, and I mentioned this actually when we were talking about greedy algorithms. Does anybody remember that? So I told you that, for example, when we studied the minimum spanning tree problem, there was this nice property that the minimum spanning trees always had, is that if I give you a minimum spanning tree, if I remove, say, an edge off the minimum spanning tree, anything that I'm left with, whether it be a forest or a tree, will still be a minimum spanning tree or a minimum spanning forest. You can also say the same thing when we talked about the single source shortest path problem. In that case, we also had that same kind of situation where the shortest path tree consists of shortest paths. So that's what optimal substructure is talking about. Now, you might say, Dan, could I have used dynamic programming there? And the answer, of course, is that yes, you can, but you would not want to do that. That's what I'm not recommending you do. But you most certainly can take advantage of that. But I must stress that the only reason why we can use those greedy algorithms the way we did is because of that greedy choice property that we had. Our selection criterion always led us to a global optimal solution. This, however, does not guarantee such things. Greedy algorithms are actually far more narrow condition, because notice that in the greedy algorithm, every single time I make a decision, I had to make it at that specific time. Here, I'm combining optimal answers to smaller problems. So it has a very different formulation, but they're kind of related in a different way. But are there any questions about the principle of optimality? You're going to see how this is going to play out when we start looking at our proper example next. So if you're not sure what this means, you're going to see how it plays out when I actually try proving a problem has this property. So the first example we're going to look at is called zero on knapsack. We actually defined this in a previous lecture. Just as a reminder, we have n items, each with a weight, Wi, and a profit Pi. And there's also this knapsack capacity, right? There's also a knapsack capacity. And our goal was to pack the knapsack with items from my collection of items I have from my input. And I want to maximize the total profit of the knapsack by selecting some subset of the items so that they fit in the knapsack, right? So just, if you're not sure about this, just remember it from the other day. So remember, we're just trying to compute a knapsack. A little squeaky there. Compute a knapsack I prime, which is going to be a subset of the items. I'll call it I. So that the sum of all the weights, if I include an item in the knapsack, I set this x value to 1. If I don't include it, I set it as 0. Such that the sum over all of the items, when I compute them with their weights, is at most W. And remember, we want to maximize the total profit. So remember the other day I formulated the idea of us having this subset of items, this I prime, as an array X, where I had each of my positions, where each one indicates whether I include the item or not include the item. That's what these Xi values are. Now, the thing that makes this problem different from the fractional knapsack problem is that, remember, in the 0-1 knapsack problem, each one of these Xi's has to be either 0 or 1. It can't be a number in between 0 and 1. So that day when we looked at fractional knapsack, I allowed it so that you can take a fractional piece of an item as opposed to either it's everything or nothing. So I must stress that this problem is actually, it is indeed a harder problem than the one I talked about the other day. So this is I'm going to tell you that this is a much harder problem. In fact, even finding an efficient, as in a polynomial time algorithm for this problem that exactly computes the optimum of every single time, we don't know how to do that. Believe it or not. So I must stress that this is a much tougher problem than the fractional knapsack problem, which we have a very efficient algorithm for. So seeing as we're out of time for today, what we'll do is when I come back, we'll talk about 0-1 knapsack. And depending on how much time we have, I may give you one more example to read over the weekend after I cover 0-1 knapsack, okay? So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.